everyone, in this video we're going to be talking all about polynomial functions. So I'll actually break this down into two parts, and in this video we're going to identify polynomial functions and their degree, and we will be graphing them using transformations. So here is our formal definition for a polynomial function, and I will do my best to make it make sense to you. It looks like a lot, but let's break it down. So this here is the form of a polynomial function. And let me explain these parts. So f of x is just f is the name of our function. X is our one variable, okay? And it looks like a sub n times x to the n plus a sub n minus 1 times x to the n minus 1 all the way down to a sub 0. Now all of these a's, these are all going to be numbers. So these are constants. So when you see an actual polynomial, these are going to be numbers, and we call them coefficients. Okay, so when they are being multiplied by x, by our variable, we call those coefficients. And then this degree here, so this number n, this is what we call the degree of our polynomial, and it is the highest power on x. So you're going to, most of the time, have quite a few terms with x in them, but it is the largest exponent, highest power. And so that's the degree of your polynomial, and it is important to know that to make it a polynomial, the degree has to be greater than 0 or greater, so non-negative, and it has to be an integer. So what that looks like is if you are working with a polynomial, the degree is 0 or more, and it has to be an integer. Okay, so these are the possible degrees. It could be anything bigger than this, but 0 or more, and it has to be integers. It can't be like fractional numbers or negative numbers. And so that's the degree, and then notice any term after that highest powered x term, this number is just smaller. A lot of the time it'll be the next number lowest, but sometimes those terms are missing, so it's just smaller than whatever number n is. So for example, if n is 5, this might be x to the 4th, all the way down to the last term as just a number, just a constant. The leading coefficient is this number in the front, the very front right here. This is the leading coefficient, and this whole thing right here, this whole term is called the leading term. And then the last thing to mention is that for a polynomial function, you can plug in any real number, and that's your domain, because when you do that, you will get real numbers out of the function. So any real number you plug in will produce a real number. Okay, so let's jump right into this example. We're going to identify the polynomial function. So which of the following are actually, by definition, polynomial functions? And if we determine that they are, we're going to state the degree. And if we determine that they're not, we'll say why not. And then we're going to write each one in standard form, and then identify the leading term and the constant term. Okay, so take a look at this first one. P of x is 4x cubed minus 1/2 x squared minus 7. Notice that the highest power on x is 3. That is a positive integer. And then we have an x squared term. There's no single x term, and then we just have a constant. And so this is a polynomial function. It meets the definition, the criteria to be a polynomial function. The degree is the highest power on x, so the degree is 3. It's already in our standard form, which was our a sub n x to the n plus dot dot dot. We start decreasing the power on x until we have a constant term in the back. Notice the -7 is the constant. So the leading term is the term in the very front. So the leading term is 4x cubed, where the 4 is the leading coefficient. So the whole thing is the term, but the number 4 is the leading coefficient. And then that -7 in the back or the 7 getting subtracted, that's our constant term. Constant if you don't see an x with it. Let's try this one. Okay, let's take a look. This has x to the first power, this is a constant, and then we have x to the 4th power. This is a polynomial. It fits the criteria to be a polynomial function, and the degree is 4 because that is the highest power that we see on x. Now to write it in standard form, we want to start with the highest powered term, the leading term. So this right here would be standard form. negative 5x to the fourth, because that's the highest power on x. We write that first, and then we start decreasing. Next would be x, because decreasing the power on x, there's no other terms with x, so that would be our next one, because here's what you would do normally. So let me just show you what's not there. There's not an x cubed term, there's not an x squared term, but there is just a regular x term. And then the last number is always your constant. So this is standard form, but if there's just 0 of those terms, don't take your time and write them there. You don't need that. And then the leading term is a negative 5x to the fourth, and the constant is 3. How about this one? Okay, so g of x equals cubed root of x. Is this a polynomial function? No, this is not a polynomial function, and it's because the power on x. If you rewrite your cubed root here, if you don't know this, let me just tell you really quick. If you have a radical like this, you can rewrite this as a fraction exponent. So the number right here on x, the power on x, goes in the numerator, and then that little index, this right here is called an index, this goes in the denominator. And so that's why we got 1/3 power, because there's an invisible 1 right here. So x to the 1/3 does not work out for our polynomial function definition, because this is not a non-negative integer. 1/3 is not an integer, which was required for us to have a polynomial function. Alright, how about this one? H of x is x cubed minus 2 over x to the fourth plus 1. What do you think? Okay, if you're thinking no, it's not a polynomial, you are correct. Okay, so it's not, and because it's actually the quotient or the ratio of two distinct polynomials. The numerator itself is a polynomial, and so is the denominator separately, but together divided like this, they're not, it's not a polynomial function. Okay, how about this one? G of x equals 9. Is this a polynomial function? And it is. So this is a polynomial function, even though it's just the number 9, and here's why. If you want to rewrite 9, 9 is the same as 9 times x to the 0. Because, let me tell you this also, if you didn't know this, x to the 0 is 1. Any number to the 0 is 1, so except 0 to the 0. And so this is x to the 0, and so we still can call this a polynomial function, but we'll call it a non-zero constant. So it's degree 0. Okay, one more here. H of x equals negative x cubed times x minus 3 quantity squared. This one is a polynomial function, and how you could actually tell is if you want to multiply this out. So you'd have to FOIL this first. You would rewrite this part as x minus 3 times itself. You would multiply or FOIL that out, and you would get x squared minus 6x plus 9. And then you would distribute this negative x cubed to all of these terms, and that's why you get negative x to the 5th plus 6x to the 4th minus 9x cubed. So quick reminder on exponents here, you add the exponents when you're multiplying the same base. So what happened right here is x to the 3rd times x squared was, and this one's just negative, so I brought that with us. That's negative x to the 3 plus 2. That's where the 5 came from. Same thing with the next one, the negative x cubed times negative 6x. That's going to be positive because the two negatives divide out. That's going to be 6x to the 3 plus 1. You add the exponents. This one has an invisible 1, and that's where the 6x to the 4th came from. Okay, so the leading term is negative x to the 5th. The degree is the 5, so degree 5 polynomial, and there's no constant because notice all the terms have an x, so no constant term. Okay, so let's go ahead and summarize some of these properties about our polynomial functions. So just for degrees 0, 1, and 2, and then no degree, that would just be the zero function first of all. And what that looks like is just the x-axis. So that one's not too critical. It's ones where our degree is something 0 or more that we're pretty much interested in. So that one for degree 0 looks like just a constant term, and therefore we call that the constant function. And it's just a horizontal line when you graph it, and that goes through the point whatever a sub 0 is. And just so you know, when it has one term like this polynomial is called a monomial. Mono meaning one. And then degree 1 polynomial function looks like a sub 1 times x plus a sub 0. There's just a number times x plus another number. And this one looks very familiar, hopefully, as a linear function or a line. This would be like y equals mx plus b, if that sounds familiar. And so this is a line going through your y-intercept of 0, comma, whatever a sub 0 is. And the slope is the number in front of x. So in this case, it's just what we're labeling as a sub 1. And then degree 2 polynomial is going to be this one here. And it has x squared as the highest power. And then we have x and then a constant term. This one hopefully also looks familiar. This one is called our quadratic function. And when we graph that, we get a parabola. Okay, and then based on leading coefficient, the number in the front of x squared depends on if our graph is going to open up or down. We talked about this previously, but the graph will open up if the leading coefficient is positive and down if it's negative. So what we're going to be doing a lot is graphing these polynomial functions. So if you have the graph of a polynomial function, it has to be what we call smooth and continuous. So smooth, meaning there's no sharp points, and continuous, meaning you wouldn't pick up your pencil when you draw it. And so this one here is the graph of a polynomial because it is smooth and continuous if you draw it. This other one over here is not a graph of a polynomial function for quite a few reasons. There's these sharp points, we call them corners, or this really kind of tight point here we call the cusp. There's holes and gaps in the graph. You'd have to pick up your pencil to draw it. So this is not a continuous or smooth curve. So it could not represent a polynomial function. So what we're going to do now is we're going to talk about this power function, and why we're going to spend some time on this is because if we can identify what happens with just this term right here. So notice this is our function f of x equals a times x to the n. This will tell us a lot about the rest of our polynomial functions. So if we could just focus on this like leading term as a function itself. So degree n is the degree of this power function, and then a is just some constant real number. And so pretty much imagine this as your polynomial, but we're not putting the rest of the terms, and we're just kind of focusing on the first term, and we call that the power function. So here's some of the things we can tell from a power function. If it's even, and we've talked about this previously, the graph has symmetry, and it is with respect to the y-axis. So your graph would look like it's mirrored left and right of the y-axis. The domain is all real numbers. The range is going to be 0 or more, so non-negative. And then the graph is always going to have the following points: -1, 1, 0, 0, and 1, 1. And think about that. If you were plotting those points, they would be mirrored across the y-axis. Okay, so now what we're very interested in is how the graph of our polynomial functions are going to look. So if we can just focus on our power function here, where this number here as the degree is even, then here's some important parts. We know that the graph is going to look like it's steeper on the left of -1 and the right of 1, but then it's going to look like it's starting to flatten out closer to the origin. So those graphs start to look like this. So let's say this was x squared. Well, we know that one. That one is our parabola, right, like this roughly. But if we get larger on n, on our degree, but it's still even, it actually starts to look like more like this. So it's still kind of parabola shape, but it's more flat here, and then it's steeper here. My drawing's pretty bad, but hopefully you're kind of getting the idea. And then what's really important is the end behavior. So what this means is, what is the graph doing as we keep going toward infinity, negative and positive. So if you think of your x-axis, and if you think about, as I plug in numbers all the way toward infinity, all the way toward negative infinity, what's happening to my graph? And so this says, whether you're going toward negative infinity or positive infinity for x, your function, remember f of x is your y values, your function is going to go toward positive infinity. So that means your graph, as you go all the way toward infinity and plug in numbers, left and right, the graph is going to go up. Okay? Infinity for y is up. Okay? And so anything else could happen in between. The graph of your function can do a ton of other things in between. It could go like this. All these other parts to this function could happen. Oh, that part's, let's fix that. Remember, it has to be smooth. Okay, so like that. And then it could do that, but it's going to go up toward the left and up toward the right at the ends. And that's for an even degree on our highest power for x. Okay, so now let's take a look at what happens when it's odd. So for an odd power function, so same function, but now this number is odd. This is an odd number. It's now symmetric with respect to the origin. So your points look like they kind of mirror across the origin. Domain and range is all real numbers. The graph contains the same 3 points, negative 1, 1, 0, 0, 1, 1. And then here's what happens as we go to the ends, and then also the steepness. So it's going to look steeper again on the left of negative 1 and not on the right of 1, but it's going to look flatter as we get closer to the origin. But the end behavior, take a look at the difference now. Okay, as x goes to negative infinity, then the y value, remember this is y, also goes toward negative infinity. Okay, so that's looking like your graph is going to go down toward negative infinity as you get closer to plugging in very small numbers. And then as you go toward positive infinity, your graph is going to look like it's going toward positive infinity as well, your y value. So it's going to look like it's going up. And so once again, anything could happen in between. The function could do a lot of other things in between. But on the ends, it's looking like it's going down toward the left and up toward the right. So now let's try a few examples. So we're going to graph some polynomial functions using what we just talked about and transformations that we've learned in the past. Okay, so take a look at this function, 1 minus x to the 7th power. Okay, so it would be better to rewrite it in standard form. So negative x to the 7th would be first. There's no other terms with x in them, and so the next and last term would just be the constant 1. Okay, so then if we kind of just use what we learned a few minutes ago, we can plot the 3 points we know are going to be on all these graphs. Notice this is for the power function x to the 7th. We're going to add the plus 1 in just a minute. So we plot negative 1, 1, 0, 0, and 1, 1. And it's looking like it's kind of flat. It's not exactly ever flat because it's not going to be the same values in the middle here, but it's looking a little flat in the middle, and then it's pretty steep on the right of 1 and on the left of negative 1. Okay, so that's x to the 7th. This is what we were just talking about. This is a power function. But our polynomial has an extra piece to it. It has actually 2 extra pieces. It has a negative in front and a plus 1 in the back. So that just this part was our power function. So our power function. And now we're going to add the transformations to it. Also, one more thing to mention is our end behavior. Notice that because it's an odd degree for our power function, it goes down toward negative infinity here and up toward infinity here. So down left and up right for this odd degree. And so now let's go ahead and apply the transformation from putting a negative 1 in the front. And remember that transformation? When we learned this before, negative like f of x, let me just write it here. If we had negative f of x, it would flip or reflect our graph. So this transformation is a reflection. And specifically, it reflects the graph across the x-axis. So notice, if you could take your graph here, pick it up, and flip it over the x-axis, then you'd have this new graph. And so the last thing we have to do is add that +1. Remember what that's going to look like? It's going to shift your graph up 1 unit, because that is this transformation where we have a vertical shift up. So we're going to take our whole graph, and we're going to move all the points up 1 unit, and then plot our new function. And so that is our polynomial function, negative x to the 7th plus 1, using transformations of this power function. Okay, one more then. F of x equals 1/2 times x plus 1 to the 6th power. Okay, so take a look. Notice that this is an even degree polynomial function. So the power function, so notice this is your power function here, x to the 6th, even degree, so it is going up to the left and up to the right, the end behavior. As we go toward the negative and positive infinity on the x-axis, the graph goes up, both left and right. We plot our 3 standard points, and then remember it kind of does this flatten out thing in the middle. It's not exactly flat, but it just kind of looks like that. And then it gets steeper on the left and the right of 1. Okay, and then we have to add our transformations. So take a look, we have 2 transformations. We have a +1 getting added to x, and then a 1/2 multiplying our whole piece with our x to the 6th. And so we'll start with the +1. Remember that one. That looks like this transformation where we go, actually that one's not to the right, where we go left, h. So because it looks like +1, we actually pick up our whole graph and move it left 1 unit. So all the points move to the left. And then we apply one more transformation. Remember how that one goes? If you have your a times f of x, it's going to look like a vertical compression because this is a fractional amount less than 1. We talked about this previously, but if the number in the front is between 0 and 1, it's going to look like it's kind of smashing the graph down, compression. So it's a little hard to tell, but if you can see it, it's less stretched out. It's more kind of compressed or smashed down slightly. And you can take your 3 points and notice that all the y values get times by 1/2. So 1/2 of 1 over here, 1/2 of 1 over here to give you your new points. And then this is the graph of our polynomial function by using our power function and applying transformations to it. Alright, so that's going to be it for this one, and in the next video we're going to continue talking all about our polynomial functions and graphing them.